Go ahead, please.
Thank you, Dina. Good evening. We have an InReach presentation this evening, but before we start, I want to make a couple of announcements. Number one, those members who attend 5 out of 9 InReach events between March and June will be receiving a InReach participation certificate. And so we encourage all of our members to attend the InReach events. And also our next InReach event is actually a special presentation by Dr. David Buckley from South Africa on Southern African Large Telescope on May 21st, Saturday at 2 o'clock special time. So we encourage all our members to attend that May 21st, 2 o'clock presentation by Dr. David Buckley. So with that, let me introduce tonight's presenter. Tony Gojanovic has been a member of Denver Astronomical Society for, believe it or not, 47 years. He was a recipient of Van Nathan Hansen Scholarship when he was in, I guess, in high school he started. Tony has interest in the history of science and astronomy, and specifically Albert Einstein's special and general theories of relativity. And that is his presentation tonight. So Tony, please proceed.
Okay, thank you so much. Appreciate it. So thanks for the introduction. Let's go ahead and get started here. And so yes, as Mehmet said, I have been a member for about 47 years off and on. I'm not much of an observer. I really don't get my telescope out too much. I have a couple of them, but they always seem to just sit in the basement. But I'm really more interested in the history of science and astronomy, particularly like how ideas are transmitted through culture and stuff like that. And I also like computational astronomy. So I like, what computers can do with, astronomical data, and also how you can like image stuff that we can't see just using some principles of math and science. So it's kind of interesting from my perspective. A couple of years ago, I took a course in special relativity from Stanford University. It was an 11-week online course. And I'll tell you what, it was probably one of the most interesting courses I've ever taken in my life. I mean, it was just interesting, and actually it was kind of bizarre too. So I always heard about it. I never knew anything what it was or anything about it. So I took the course and I just was hooked on it. So I'm going to talk a little bit about that today. So kind of an overview, I'm going to explain the special and general relativity of Einstein's, just very general, broad terms. I also want to provide a little bit of a historical context for some of these discoveries of his, the kind of the time period. And a big part of this was, eclipses and how they helped to verify some of these principles that Einstein had come up with. Along those lines, we're going to journey with a early 20th century solar eclipse expedition. How did they do eclipses? How did they do scientific studies back then? It's actually pretty fascinating. And at the end, I want to provide resources on how to replicate this famous solar eclipse experiment from an amateur perspective. So you can actually do it yourself. It is possible doing it during an eclipse. So we're going to talk about that a little bit as well. Today, astronomy is a lot different than it was a century ago. I mean, we've discovered black holes, gravity waves, neutron stars, exoplanets, dark energy, dark matter, universal expansion, cosmic microwave background radiation even. Here's a picture of a black hole taken from the Event Horizon Telescope that was imaged. Exoplanets, here's some conceptual pictures of what other planets might look like around other stars. And this is just the start of it. This is just an iceberg of what we've captured. And a lot of this stuff is pretty fantastical. You know, I hear about this stuff and I'm like, really? That truly exists, you know? And it just seems like every day there's always something even more incredible that's being discovered. And, you know, we have a wide variety of telescopes today and instruments to observe the universe. This is just a small sampling, but, you know, we don't have just stuff on the ground, you know, observatories. We have stuff in outer space as well. And we're not just looking at the visible spectrum either, right? I mean, the visible spectrum is the stuff that we can actually see, but there's the stuff like, you know, gamma rays and X-rays and ultraviolet that we can't see, but we can, you know, get information with other types of instruments, and the infrared and microwave as well. So, you know, somebody said once, you know, visible astronomy is just like looking through a narrow slit in a doorway, you know, when there's actually a lot more out there that we can obtain with different types of instruments. You know, and a lot of it we take granted for what we know, but it really wasn't always this way. So, you know, if we look a century ago, so it's 2022, you know, 1922 or earlier, they had questions that they didn't know answers to like we do today. You know, was the universe static? Okay, did it change or did it evolve? Okay, is there one galaxy or is there a sea of island universes? That wasn't known back then. Are nebula clouds of gas or galaxies composed of stars? You know, even that fact, I mean, today we know there's, you know, billions of galaxies out there, and each are composed of billions of stars, but back then that was an unknown fact. You know, how big is the universe? How old is it? You know, is the sun the center of the galaxy? Okay, that was a question that was proposed back then as well. Is there a cosmic distance ladder? You know, how big is the universe in the age? And even something as simple as why is the sky dark at night, which is called Olber's paradox. You know, that was a question people didn't have an answer to. But this was also kind of the beginning of big data, because people were interested in this and they started, you know, using different instruments to gather information about this. So, you know, you can characterize that period in the, you know, early 1900s as kind of the golden age of astronomy. You know, cameras became standard equipment, allowing detailed study. So people were hooking up these, you know, large cameras to telescopes, taking pictures, and then later on actually analyzing, you know, the data or the picture. Okay, taking your time to do that. You could put a spectrograph on a telescope. So a spectrograph breaks down light into various components, so you can tell something about the composition of an object. You can even say something about if it's moving away from you or not. And then there were some ideas like general relativity, you know, gave us some ideas into the cosmic structures. If you're interested in learning more about this, there's a great book called The Glass Universe by Davis Sobel. And she wrote about these, what are called women computers. And a person who's a computer back then was somebody who basically analyzed data. So, you know, there was a Harvard University basically employed these women to look at these plates, you know, thousands of them, to analyze and classify data. So if you're interested a little bit more about that period of time, this is a really, really excellent resource to look at. Okay, let's see what we got. Before I go on, I want to talk a little bit about telescope types too. There's two essential types. One is a refractor and one is a reflector. So a refractor is, oops, go back, was pioneered by Galileo in 1609. And the way it works is it refracts light through a lens to an eyepiece in the back, okay? The other type of basic telescope is a reflector. So it actually takes a light and reflects it by a mirror to into another little mirror into an eyepiece. And this was something that was pioneered by Isaac Newton. Those are the two basic types of telescopes. There's lots of variations around those telescopes today, and each has their own advantages and disadvantages. You know, one of the biggest ones with the refractors, it has this what's called chromatic aberration, this kind of color fringing around it, around an object. Reflectors, they don't have that chromatic aberration. And price-wise, you know, today you can buy a reflector which is pretty substantial size, whereas a refractor is a little bit more pricey. So those were the kind of the fundamental types of optical telescopes, and we'll talk about how they were used. You know, the early 19th century was kind of the last of the big refractors. So, you know, we have Chamberlain, which was the 20-inch, Lowell, which was a 24-inch Lick, 36-inch, and of course the gigantic Yerkes refractor. So these were astronomical instruments, but they also have a limiting factor to them. You can't, there's a size that it just becomes more and more difficult to actually make them practical. So this was kind of the last of the big refractors in a way during this period of time. And it was a paradigm shift in observing. So, you know, two astronomers, James Keeler and Heber Curtis, you know, came up with this idea of using these reflectors. So here's a 36-inch reflector at the Lick Observatory, which was used from 1895 to 2010. So it was actually used for a considerable amount of time. And you could take some incredible images with these type of instruments. And they really kind of proved that reflectors were a viable scientific instrument. A lot of people at first, you know, I was reading about this, they're like, oh, this will never work. And these, you know, just kind of goofy instruments. But in the long run, you know, the reflectors kind of took over. Personally, I'm partial to refractors. All the telescopes I own are refractors. And why is that? For the simple reason that I think they look cooler than reflectors. Nothing, I mean, it's not a technical reason. It's just that I kind of like them better. I just think they're just neater looking. But a lot of people use reflectors today. And, you know, it was the rise of the reflectors, as I say. It was, you know, the 60-inch Mount Wilson, you know, 60-inch mirror, you know, reflecting starlight in 1908. The famous 100-inch was built in 1917. And one of the, you know, I like this, astronomical telescopes were the impossible combination of the scale of a battleship and the precision of a microscope. So, you know, just reading how they built these, and if you've ever visited one, I mean, it's just gigantic pieces of iron and everything, but you can move it, you know, with your hand or whatever like that. It's just incredible. Of course, the famous 200-inch Palomar, which was built or commissioned in 1948. You know, it's kind of the epitome of the reflectors. Of course, there's larger ones today. But if you're looking for a nice resource to learn about this, there's a story called The Perfect Machine. Excellent, excellent book. Very detailed, maybe a little too detailed at some point. And also this book by Marcia Bartusek, you know, The Day We Discovered the Universe. Excellent book also about how things changed during this period of time and how different instruments came to play out. So that's kind of the context of the early 19th century in terms of the type of instruments that were being used and the type of technology. But, you know, there's the technical part. There's the nuts and bolts, right? And, you know, William de Sitter, he was a famous mathematician and, you know, did work in astronomy. You know, he said, never in all of history of science, you know, has there been a period where new theories and a hypothesis arose, you know, flourished and were abandoned in quick succession in the last 15 or 20 years. So it's not just about having great technology, but it's about having great ideas as well, stuff that were just amazing. And that's why that's why I'm so fascinated with Einstein, because his ideas were truly revolutionary. So, you know, we have Albert Einstein, 1879 to 1955. He revolutionized the way we look at the world and the universe from a scientific standpoint. But I was also reading about, you know, Pablo Picasso. You know, he's a famous artist, and he was 2 years younger than Einstein, and he really revolutionized the way we look at the world and the universe from an art standpoint. There's an excellent book. It's called Einstein, you know, and Picasso, which talks about, you know, how they really changed the way we think about things. The book isn't so much about like how science influences art or art influences science. It's rather that this creative energy or spirit really comes from the same source, but maybe manifests in a different way. And it was really a break from the past and an introduction of what's called a new schema, or way of looking at things, and new orders of perception. You know, I have a side interest in art history as well. And, you know, sometimes people will look at a Picasso painting like this one here, and they'll say, well, that's ridiculous, and, you know, it's meaningless, it doesn't mean anything. But you could say the same thing about Einstein's theories as well. I mean, if you look at things like time dilation and length and time are not constant, you could say the same thing. I mean, how absurd is that? But, you know, the difference is with Einstein's theories, it's based more in mathematics, which is a language that we can really relate to. And, you know, Picasso's in modern art is got a little bit more fuzzier language. There is a language that can describe this so we can have a conversation, but, you know, principally it's a similar type of movement. Anyway, if you're interested in science and art, that's a really, really good book. So also Einstein, you know, he's got new ideas, and it's Einstein versus Newton in a way. You know, Einstein was, let's call him the enemy, and I'll talk about that in a minute. But mass and energy are interchangeable. That's the famous E equals mc squared. Whereas, you know, Newton was like, well, mass and energy are different. Okay. Space and time create a four-dimensional universe. Space and time are really fundamentally different. Time and measure is suspect. In other words, time and measure may not be constant in all frames of reference. Whereas Newton is like, well, time and measure are constant. And, you know, Newton is, or you know, Einstein is, gravity is not a force, but a geometric distortion of this thing called space-time. And, you know, Newton's more like, well, gravity is a force acting between two bodies, okay? So there are fundamental differences here. And, you know, Newton's theories work very well in a wide variety of applications. And people were very, you know, they're not willing to change. You know, here's Newton, who's been around for hundreds of years, his ideas, and now this guy comes in. And I call him the enemy because, you know, another part of this era was World War I, you know, and Einstein was German, and that was not looked favorably upon other people, especially, you know, the English at the time and so forth, because they were at war with them. So, you know, one of the things I also forgot to mention is people like Einstein and Picasso, they were incredibly courageous people because they brought something brand new to the world. And that's really hard to just stand up to people and say, here's something new, and, you know, kind of be ridiculed for it. So anyway, that's kind of where the situation was at that time. There's a lot about Einstein I didn't know about, which I thought was kind of interesting. You know, Einstein, most of us have this image of him with the crazy hair and, you know, a t-shirt that has Einstein's picture on it or whatever, but they really don't know much about him. You know, he was born in Ulm, Germany. He studied physics and mathematics. His most significant works were during employment in a patent office. So some people know that He worked in a patent office for, I think it was 7 years, while he was trying to find work elsewhere. He was also a nonconformist, and he was non-obedient or differential to other people. Okay, so he had a very strong will about him. And he wasn't a great student, but he had a brilliant mind. There's this, if you have kids and they're not doing well in math, sometimes you hear, well, Einstein failed math, so I guess it's all right for me to fail it too, right? He didn't fail math because he didn't know math. He failed math because he didn't go to classes. He just didn't find it interesting what his professors were teaching, so he decided not to attend in a lot of cases. And that kind of hurt him academically. But this is, to me, the most remarkable thing about Einstein. And this is called the miracle year of 1905. And in this year, he came up with the following. So he was 26 years old here. So he came up with this idea that, that light is a particle, kind of this photoelectric effect. His dissertation was the size of molecules in April of 1905. So I read somewhere this is one of the most referenced papers in science. Brownian motion. This is basically proving the existence of atoms in May of 1905. And then special relativity, this idea that time is suspect in June of 1905. And then the energy mass equivalence in September of 1905. So here we have 5 revolutionary, massive works in a period of from March to September by a single individual, okay? I mean, to me, that's unbelievable. A lot of academics spend a lifetime trying to come up with one original idea, and he came up with 5 in a period of a year. So this is, a lot of people know him for like this E equals MC squared and maybe even special relativity, but he did a lot of other things that were very influential in science. And the whole idea of special relativity, and this is a very just kind of just a quick snippet, is that light is constant, the speed of light is constant, but time and measure are not, and it depends on one's frame of reference. Okay, so there's a famous thing called time dilation, and the thing is if you put a person on a rocket ship and they're going close to the speed of light, and a lot of this stuff happens when you're traveling at speeds close to the speed of light, the time will move differently depending on the observer or the observed. So if you both start your clock at the same time, and this person goes off on this rocket, and they're going very, very close to the speed of light, let's say, and by the time they come back, this person's clock will have gone much longer than this person's here. So the clock on the rocket is actually going slower. It's not going slower to the person on the rocket. The clock is going the same speed, but to the person outside, it actually appears to be going slower. And the person on the rocket, their clock is ticking away fine, but looking at a person outside, their clock seems to be running a lot slower. So, first time I heard this, it's like, really? That's a true fact? That really happens? And it is true that does happen. Let me give you a quick example here. So, the life of a muon. So, this is a cosmic, you have the Earth's atmosphere here, okay? And a muon is a kind of an elementary particle that's caused by cosmic rays interfering with other particles in the Earth's atmosphere. So the muon basically has a life of 2.2 microseconds. And its average velocity is 0.998 the speed of light. So it's almost traveling at the speed of light. So if you figure it out, in its life, it should travel about 660 meters, okay, before it completely fizzles out. So, few football fields, several football fields. But if that's true, then how come we can see them on Earth? And you can actually detect muons yourself. You can build a kind of a cloud chamber using a fish tank and stuff. There's a bunch of YouTube videos on it, but you can actually see them here on Earth, and they're coming from 10 kilometers away. Well, if they last 2.2 microseconds and they're only traveling 600 or so meters before they die, how can we see them? Well, relativity kind of gives us a clue. So from our perspective, due to this time dilation, my clock actually elapses 30.3 microseconds for the muons 2.2 microseconds at those velocities. So in about 30 microseconds, that muon will travel about 10 kilometers. In other words, it'll make it down here. But if I was the muon, okay, traveling at that speed, I'm not moving at all. Actually, I'm standing still, and the Earth is approaching me at almost the speed of light. Well, at that speed, the distance is only 600 meters. So special relativity says the distance is also compressed according at those kind of velocities. And because of the length of that contraction, it gives me long enough to see the Earth in 2.2 microseconds. I mean, to me, that's absolutely insane, crazy type of logic and math, but apparently it does occur. And that's in a general case where things are traveling at a constant speed. So in 1915, so 10 years later, after special relativity, Einstein came up with general relativity, which is what happens when things are in an accelerating frame of reference, specifically like within a gravitational field. So again, this is probably considered the birth of modern cosmology and astrophysics, this very paper here. And if you're really interested in understanding this from a layman perspective, there's a really, really good book by Ron Cohen on general relativity, which I highly suggest. It's not too long, and it's very, very simple and entertaining and very clear cut. Well, that's all nice to have these theories, and keep in mind that Einstein didn't come up with these theories based on any observations. He wasn't looking through data and said, wow, here's what's happening. This came out of his head, and that's another absolutely amazing thing that occurred here. Here's a trivia fact. One of his friends, David Hilbert, famous mathematician as well, he actually attended a bunch of lectures from Einstein prior to 1915. And he actually tried to solve some of these problems with math. And it turns out that he actually came up with the identical results to Einstein's. He presented his results on November 20th, and Einstein presented his on November 25th at a conference. So technically, due to scientific precedence, Hilbert could have claimed credit for general relativity, but Einstein and Hilbert were friends, and Hilbert let Einstein have the credit for it, much to Einstein's relief. He'd been working on it for at least 7-8 years, and it would have been kind of a shame, I guess, but that's the way it goes sometimes. And also, if it wasn't for the theories of special and general relativity, just a side note, our GPS devices wouldn't work properly. So because of the speeds of satellites and so forth, I mean, they're not approaching the speed of light, but they're fast enough that this time dilation does occur. And if they don't take that into account in the software, all our GPS devices would be off, eventually by feet, and then meters and kilometers and so forth. So today, Einstein's theories are pretty well verified. I'm not going to say proven, but back then it's like, what are you going to do to prove this? So, you may also see something like the bowling ball universe. So Einstein's theories of space, time, and so forth basically state that you have this kind of gravitational well. It's called the bowling ball universe. So you can imagine a bowling ball like on a trampoline, and it deforms, this space-time around it. And how would you verify that this is actually happening? So you can imagine a beam of light, for example, coming through here. So it's actually going to be distorted somewhat. And more generally, the theory says that if you have a large object like the sun, it really warps this space-time, and you're looking at a star here, because of this warping effect, it's actually going to be here. There's a more general way of looking at that. It's called gravitational lensing today. And you've got this, deformation in space-time, due to some very large object like a galaxy cluster. And by the time these light rays get to you, okay, they're going to be distorted from their original position. There is actually an object called Einstein's cross, and it's in Pegasus. So if you're interested in trying to find this or even image it, this would be a very, very good object to actually look for. So this is an object in that the light is actually being deformed by a quasar, and it's actually bending the light. So today we know this is actually happening, but back at the turn of the century, last century, they did not know this. So back in 1911 is when Einstein started formulating this general relativity. He predicted a deflection, passing of a light by the sun would deflect by 1.7 seconds of arc. So if you don't know what arc is, this would be roughly 1,000th the width of the moon, which is 31 arc minutes. So 1 degree can be broken down into 60 minutes, 60 seconds. So an arc second is 1/3600th of a degree. So this is a very, very small deflection. And one of the key proponents was this Arthur Eddington. He was a British astronomer, and he was a very large proponent of Einstein. And a lot of the stuff that he learned from Einstein, because it was during the war, information was being cut off, and he got it through third-party scientists and so forth. But he was a big proponent of this, and he wanted to actually try this experiment as well. And the method is take a picture of a star field before an eclipse, okay, and then the same star field during an eclipse, and see how much the light has shifted. Okay, so that was the whole idea. So what is an eclipse? So an eclipse occurs when one heavenly body, such as a moon or planet, okay, basically will moves into the shadow or the light of another body. Okay, so a picture will look like this. So solar eclipse, okay, you've got the moon, and basically it's between the Earth and the sun, and it leaves a little shadow on the Earth. And there's different type of eclipses. There's partial eclipses. Okay, sometimes you just see a part of it depending where you're at. Full eclipse, okay, that's where the sun is completely blocked out. An annular eclipse is where, because of the position of the moon to the sun, the moon's a little farther away, so you actually just see a ring of the sun. And here's kind of a neat picture I picked up from NASA. It actually shows what an eclipse shadow looks like from outer space. And so the greatest intensity would be in the middle of that shadow there. That would be the full eclipse part. There's two aspects to an eclipse, the Umbra and the Penumbra. So the Umbra is the more focused shadow, and then it kind of becomes a little bit more diffuse as you go out. So those are kind of the basic components of it. There's a similar analogy for lunar eclipses as well. Okay, solar eclipses don't occur as often. Lunar eclipses are a little bit more frequent. And lunar eclipses, you can pretty much view them with a telescope or binoculars or naked eye, but just a caveat, solar eclipses, even though you're looking at the sun that's been blocked by the moon, it's really super dangerous unless you have the right equipment. So you never want to look at it directly. So, okay, so this Eddington's like, okay, we're going to go ahead and have an expedition, and we're going to test this theory doing an eclipse. So it was organized by a guy named Sir Frank Watson Dyson, who was the Astronomer Royal at Greenwich Observatory. And basically, they were going to go to two places. One is Brazil, and they sent these two people, Andrew Crommelin and Charles Rundle Davison. He was a computer, so he was also a data analyst in a way. And then to Africa, they were going to send Eddington and this other individual here as well. So they were going to set up their telescopes in these two positions, okay, and try to actually capture these images and see if they can measure this deflection. So here's kind of basically how the expedition went. They left Liverpool here, went to a small island here. Then the team split up. One went to Brazil, and one went off to the coast of Africa. So they started in March 8th, and the eclipse was actually in May. So, I mean, today, obviously, we can be anywhere in the world fairly quickly with an airplane or whatever, but they had to go basically by ship, and it took a long time to get to these places, and it was complicated because you're bringing astronomical instruments as well. But they did manage to get to these locations, and this is basically what the eclipse path looked like on May 29th. So the duration of the eclipse was actually one of the longest recorded in the history of eclipses, but it actually went through the two locations that they had set up their stations at, okay? The shaded part here is kind of the not the primary eclipse, kind of the partial eclipse zone. A total eclipse actually occupies a very thin swath of geography, so it's pretty important to be in the right place at the right time. And here's what they look like in the setup in Brazil. So Brazil, they had a astrograph. I believe it was a 12-inch astrograph. And they also had a 4-inch refractor. So they didn't actually bring the telescopes with them. Rather, they brought the lenses with them only, okay? And then they actually built the telescopes on site. And also you can notice that these telescopes are pretty immobile. So in order to track the sun, they actually set up these mirrors here that were weight-driven, clock-drive mirrors that actually would turn and follow the sun and reflect the sunlight into the telescopes themselves. So the telescopes didn't move. They just were static, but these mirrors would actually keep track of what was going on. I don't have a picture of what the Africa location looked like, but they just had one astrograph at the African site, pretty much. In terms of weather and so forth, they had pretty good luck in Brazil. They did not have as much luck in West Africa. And here's kind of a picture of what they had. This is from the Brazil location. They actually ended up with about 23 plates that were usable. And when I say plates, the way it worked is they had these large photographic, like literally plates, like a sheet of paper, and they had a photographic film on them, and they would actually take a picture with those. From the Africa location, they only had 2 usable plates, but I don't know if you can see this very well. Actually, let me highlight this with a pen. They actually had these little marks right there. So there was a star here, and a star here. So you can actually see stars during an eclipse, and they were able to actually compare these with the same star field before an eclipse. And they were actually able to measure the deflection within the predicted limits, okay, using these plates, whatnot. And what were the expedition consequences? Well, I mean, basically, at this point, Einstein became a celebrated hero. You know, newspaper articles were written, and this is interesting. You know, stars were not what they seemed, not where they seemed or were calculated to be, but nobody needed to worry. So, you know, it's kind of something that's pretty shocking in a way. If you want to read a pretty good outline of this, there's a great book called Shadow of a Doubt. And it actually talks about this whole expedition, not only how it was done, but it also talks about the consequences. And the shadow of a doubt comes into play because this experiment was tried and to be replicated over many years, and nobody could get the same results. And also, I mean, think about how they did this. They traveled, you know, halfway across the world. They set up their stuff, you know, built their telescopes on site. Hot, humid, dry, dusty conditions, whatnot, and they didn't have any, you know, computer equipment to analyze the film or the plates or anything like that. And a lot of people were like, they must have made up the data. Okay. Well, it turns out that they did not make up the data. They actually did reanalyze some of these plates in the 70s, and they did find out that indeed they did show this deflection. And there was another aspect which is really interesting about the book is the art of experiments. There was a whole art to experiments back then that they just don't have today. So a lot of it, you know, we rely on computer technology, but these people were so involved with these type of experiments, they just had a different intuition about it and how to make it work. But this is a really, really good book if you're interested in that. Yeah, light bending over the years, 6 professional worldwide eclipse expeditions were launched. The last one was in 1973 by the University of Texas, and they were unable to get the same results. You know, today you don't really need an eclipse to do that. You can do it using radio wavelengths during daylight times. And they also have this, you know, satellites today can actually show this light bending effect, not just from stars and starlight, but even objects like, you know, planets as well. So you look at something like Jupiter, which also has a heavy deformation of space-time, you know, you can see light bending around that as well. All right, so big question, can you do this experiment yourself? And the answer is yes. So during the 2017 eclipse, an amateur by the name of Dan Bruns actually replicated this experiment successfully. And how did he do it? He used a 4-inch teleview refractor to do this, software bisque MYT mount, an 8 megapixel cooled monochromatic camera. And he practiced a lot of the photography or the imaging when the sun was just right below the horizon. So he was able to image some stars. So he was kind of able to simulate an eclipse just as the sun went down. And he compared his results to star positions from the Gaia satellite data. He claims that it took him 2 years of prep work. And he claims that he was doing this basically full time every day, just getting ready for it. Here's a picture of his eclipse photo. And basically he was tracking these different stars. Can't really see them, but these circles are where different images of stars would be. And he was not only able to replicate the 1919 experiment, he got a deflection between 1.69 and 1.81, which is actually 1.175 is the actual deflection predicted by Einstein's theory. So he was actually able to cut down the measurement error from 11% from the University of Texas expedition to 3%. And because of this, he actually won the Chambliss Amateur Achievement Award from the American Astronomical Society. So this was actually a gigantic, huge accomplishment. And there's a bunch of articles you can read on it as well. Let me see. Get back there. Yep. So let's see if this comes up. There's a sky and telescope. You can just go ahead and Google it, but he won the award. And there's also a DIY resource, NASA, on how to actually do this experiment yourself. I would say that it's not a trivial experiment at all, but if you're really trying to test your equipment and test your resolve to try to get something like this, it would be a good project. Okay. This is kind of a funny one. Solar eclipse watching has been often referred to as persistence rewarded with disappointment. And, the track of a eclipse, as I mentioned, is very, very narrow. And a lot of times you actually have to travel to different places. So the next North American total solar eclipse is in April of 2024. And Sky and Telescope actually has a lot of pretty cool tours as well. So if you can't, see it here in the United States and you have some resources to go to Egypt, you can go see an eclipse in Egypt. But there's also an Eclipse Prediction website. And this is called timeanddate.com. And it'll actually show you different eclipses worldwide for different times and dates. And a lot of eclipses happen over the ocean or in very remote places, but you can actually use this to kind of find out where you're at and so forth. And let's see what else we got. So here's the 2024 eclipse. If you're interested, trying to capture that one. You're going to have to do a little bit of traveling, it looks like. Maybe down to Texas or Little Rock or maybe even Indianapolis or something like that. But again, this is the next eclipse. And again, if you want to give it a shot and try to replicate the famous Eddington experiment, this would be a good place to do it. And that's all I have. I mean, that's kind of a quick summary of an interesting period of time and some interesting results from a very fascinating theory. That's all I got.
Thank you, Tony. Maybe you can stop sharing and we can open the the meeting to questions. If you have a question, please raise your hand, or do I see any questions? Yes, John Bickle. Unmute, please.
Yeah. Obviously, this works best if you can choose a specific star or set of stars to try and do this. I mean, obviously, you want one where it's close enough to the sun, or at least its apparent position is close enough to the sun, so that you'll see the bending. But obviously, if you pick one that's far enough away, you're not going to see as much of a bending. How did, can you describe anything what they did to try and select the targets that they would run an amateur experiment like that?
Yeah, so for the 1919 experiment, they used the Hades, basically star cluster area over there. In terms of what Dan did for the 2017, I think he used one of the stars was Rigel that he used for his target star, I guess, part of his target stars. How he decided to choose those, I couldn't really find in the literature, but I think maybe, well, actually, it probably wouldn't be such a bad idea to actually write him and ask him how he actually chose that particular star field. Because if your stars are too dim and they're too far away, or whatever, or if they're even bright and too far away, it's not going to help you much. So you really have to have something at that very thin fringe right by the sun. Detecting something in 1.7 arc seconds is pretty tiny,
Yeah.
and you have to have some pretty massive stuff. It's interesting too, 1.7 arc seconds on something like the size of the sun, but yet this gravitational lensing happens, like I think I mentioned, even around planets and stuff like that. So for an amateur, I think you're going to need something pretty bright and pretty close to that. But I think it'd be worth actually asking Dan how he did it. I'm sure he wouldn't be opposed to it. Thank you for that question.
Thank you, Tony. Next question. I see a remark from Sam Andrews. Sam, do you want to make your remark?
Oh, I just typed in something real quick, but yeah, during the period when those Eddington experiments were being duplicated and stuff, I watched and read it at the time. This is a lot of good memories. It brings back all that stuff again. So thank you. It was a very good presentation.
Well, thank you. Just I was going to make a comment also to Jack's comment there, where it says the photoelectric effect was his Nobel Prize, which is true. He didn't. To me, the relativity part is actually a bigger. I mean, it's just such a massive change in the way we look at things. But he actually won the Nobel Prize for the work he did on his photoelectric effect, believe it or not. Part of what I read is, even though the relativity is probably a bigger accomplishment, a lot of people didn't really understand it. They weren't going to give a Nobel Prize to somebody that they really didn't understand what he was talking about. But the photoelectric effect is a little bit more straightforward, I guess.
I have a question for Michael Gardner.
Yes.
Yeah, thanks. I'm kind of curious, how close were some of these stars that the Eddington folks and the others folks did? And how far away would a star be from the sun in arc seconds, roughly, where you could not detect it? So how strong is that gravitational field of the sun? Has there been any work done on that kind of thing? How far out can the sun reach that we can actually detect a displacement?
Yeah, and I think that's a related question, to John's question as well, is how far away does it have to be, and so forth. And I read a ton of it, but I didn't find anything on that. But I suspect if I looked at the DIY from NASA, that might help a little bit. Actually, the true way to do it would actually be to try to actually calculate it yourself using general relativity. But it would be easier to look it up probably. Because I don't think general relativity is a very trivial thing at all.
Tony, you said, I have a question as well. You said that professional astronomers don't need the solar eclipse to prove this relativity theory now.
Yes.
What do they do as an alternative?
They can do it during actually daylight hours. They can, as I mentioned in the beginning, the visible spectrum is a very narrow spectrum. So they can use other forms of light as well, like electromagnetic radio waves or anything like that as well. But the biggest one actually comes from the Gaia satellite, which can actually really pinpoint positions of stars very accurately. From what I was reading, that professional astronomers really don't, this kind of sound kind of glib, but they don't really care about eclipses anymore. Because in the old days, you use eclipses to study like the chromosphere and get detailed knowledge of the sun. But nowadays there's other methods to do that. So professional astronomers don't go out and use a solar eclipse to prove Einstein's, theory. They kind of leave that up to the amateurs to do, which I think is kind of a cool way to approach it. But I would say, to your question, they would either use like satellite imagery or other forms of electromagnetic waves, gamma rays, X-rays, or whatever.
Well, when you can see something like Einstein's cross
Mm-hmm.
or other forms of gravitational lensing,
Yeah.
those are good examples.
It'd be interesting that, if I can just throw out a challenge, it would be interesting to see if some astrophotographer could actually capture that gravitational, Einstein's lensing. I mean, it has a magnitude of 16.4, I think, or something like that.
That would be a challenge.
Yeah.
Mhm.
You also mentioned that GPS satellites actually take advantage of this relativity as well. And if it
Yes.
didn't, they would be off.
Correct. Mhm.
Am I right?
Correct.
How does that happen? I did not understand that part.
So there's two aspects to it. So you have a satellite going around the Earth at a very quick velocity, fast velocity. So the constant velocity actually, because of that speed, it makes it look like the clock is actually moving slower on the satellite, okay, compared to us. But there's also the height of the satellite as well. So that's subject to gravity, Earth's gravity. And as a clock moves higher and higher above the Earth, it's actually going to speed up a little bit because of general relativity. So Einstein basically said that a gravitational field is equivalent to like an acceleration of some type. We're actually being accelerated by gravity in a way. So actually the acceleration of gravity is a lot less at that height, and the clock will move differently at that height. So you've got two factors. You've got one is the speed at which it's going around, which is slowing down the clock, but yet it's actually going a little bit faster at that height as well because of less gravitational acceleration. So you actually have to take those two into account.
So where is the correction done?
I would imagine it's probably done in the software, probably on the I don't know, either the satellite or some, stations down here. Because if you measure the clock, your clock ticking here, and the one measured on the satellite, it's going to be different. Okay.
Right.
So that correction has to take some place into account to make that right.
Okay. Any
Crazy.
other? Yes, it is. I did study the GPS system before, but this is the first time I heard that Einstein's relativity theory has been applied to the GPS system. I never expected that.
Yeah, one of the things too is, I mean, even if you take an atomic clock, one that's been synchronized with one here, and put it in an airplane, you can actually show that
right
effect as well.
Yeah, I would imagine the same principle applies there.
Mm-hmm.
Okay, any other questions? Yes, Mark. Unmute, please.
Didn't the Air Force conduct one of those experiments, like 30 years ago, where they had planes going opposite directions around? I remember something about it, but I can't remember if it was a U.S. Air Force or somebody, but they did that with some really high-speed aircraft going in opposite directions at different levels and demonstrating how the clocks run differently.
Well, John
I'm sure
Bickle
they- yeah.
sorry.
Oh, go ahead.
John Bickle just put in the chat that they've done experiments with atomic clocks at sea level and on mountain tops and measured the time difference.
Yes, I see that comment. Yeah. Okay, coming back to Mark's remark about the crossing high-speed airplanes. Tony, do you have any remark about that?
I have heard an experiment where they've done it with the aircraft, but I don't know if the experiment of where they might have gone in different directions. But I wouldn't be surprised if they did do something like that, because it's a relatively simple, in a way, experiment. It doesn't cost a huge amount of money. But I haven't read anything about that, type of specific experiment. I know they have done it on aircraft as well.
It was a long time ago, probably back in the 70s, as I recall.
Yeah, that's correct. Mhm.
Yeah. And I like refractors too.
Yeah, they're cool, right?
Yeah.
The description of the muon and how it sees the Earth moving up at it and the
Yeah.
difference in time for it as opposed to us. That just blows my mind.
It actually kind of bothers me a little bit. I mean, I took this course, I mentioned, and the professor was really great. He derived all the equations and everything. And you understand the logic of it, but I can't comprehend it at all in my head. It's like, even relativity, there's no way to prove if you're moving relative to something else, if you think about it. So, if you're standing still and a car drives by you, how's that different than you're moving by the car is standing still, right? I mean, the difference because there's the car and objects around you. But if you were in outer space where there's no objects, how would you tell who's moving and who's not, right?
Well, that's why Newton is much better understood and taught than Einstein. It's much easier to comprehend and relate to Newton, the apple falling on your head, versus the light bending for the relativity theory.
I just have a hard time actually comprehending it. I'm a logical person and everything, and but I just can't somehow make it work in my head in a way. It's like, I don't know.
That's why he is special.
That's right.
Or he was.
Yeah.
Any other comments, questions? Everybody understood?
You can always email me later.
Well, there is a test at the end of this.
Yes, there will be a test right now. Pop quiz.
Yes. Well, thank you very much, Tony. We really appreciate it. You enlighten us this evening, and we really, really appreciate you putting the effort and teaching us several things here. Thank you very much.
Yeah. Well, thanks for your time. I really appreciate it. Thanks.
Okay.
I see one more thing that popped in, and I actually have this question too.
Oh, good.
David Grant says, mass warps space. And I wanted to ask about that too.
Yes, that is correct. So mass actually warps space. And there's a famous quote by John Wheeler, which I caught somewhere up there earlier. Let me look at it really quick. And basically, he said that John Wheeler was a famous physicist as well, who did a lot of work in the 50s to help actually propel Einstein's theories. But let's see what he said really quick here. Just looking at my slides. He said, matter tells space how to bend, and space tells matter how to move. So basically, yes, it is true that mass does actually bend space-time. And even your mass, the mass of you as a human being, bends the space-time around you. to a very small, insignificant amount. But yes, that is true. That it does. That is what's being, what's happening. There was actually an experiment, and I can't remember it, but they sent a satellite around the Earth, and it had these like two spherical. Oh God, if somebody can help me out with this, but they actually measured this warping effect around the Earth using this special satellite with this super precise instrumentation. But that's also another thing that's hard to believe. I can't even imagine the space-time thing, to be quite honest with you, but it's just beyond me. I mean,
Yeah.
I don't know.
Yeah.
It's also interesting to notice too that I won't take too much more time here, but when Einstein proposed his theory of relativity in 1915 and so forth, and it was verified in 1919 or whatever, it actually languished for about 30 years, kind of in the backwaters of academics. Nobody did anything with it. But it was only with the advent of better telescopes, satellite imagery and so forth, that people started taking an interest in it. Discovery of a neutron star, for example, which is explained by, to some degree, relativity, black holes, of course, and so forth. Even though Einstein wasn't a huge fan of black holes, there's something weird about those as well. But anyway, it really kind of was in the backwater for many, many years until it started getting a little bit more popular in the 60s, 50s, and 60s. Yeah.
Okay.
Very, very interesting.
Yeah, the whole topic is very interesting and challenging as well. Well, again, thank you very much, Tony. We very much appreciate, and we can end the live streaming as well.
Okay. Well, thank you so much. If you have questions, just send me an email. That'd be great.
Thank you. Have a good night.
You as
Thanks,
well.
Tony.
Thanks so much.
Bye-bye.
Nice.